Today we're going to talk about measurement and why that's so important in physics for us. Some objectives for this lecture. We want to know the difference between accuracy and precision and be able to make measurements with both. Identify and quantify causes and effects of uncertainties in measured data. We want to know why. We may have some uncertainties when we do measure things, and to record data using our international system, our SI units, and scientific notation. So before we begin, we're going to ask these assessment questions. Go ahead and pause and answer them. Once again, here is the second question. Do the same thing. Go ahead and pause and think about your answers. And a third one. Our terms we're going to focus on are going to be accuracy, precision, decimal places, and significant figures. Hopefully you've done significant figures before. I know I didn't last year in chemistry, but we will be using them in physics. Since physics is based on measurement, we know that it's really important to collect data by measuring, but what you may not realize is that all measurements have some degree of uncertainty. And when we express our uncertainty, there's usually a plus or minus, and then this small number behind it, typically. All this is saying is that to this degree right here, we're unsure after that point. The measuring system might be inadequate for some type of measurements. For example, if we have a ruler like this, it doesn't really give us the spaces in between here, but this ruler does. The measuring procedure might have some shortcomings, so if you ask a child to stand still and try to measure them, that's really hard to do, so they may be wiggling, and you are unable to capture that measurement. The environment may cause problems. Most things, when it's heated, they will expand. Not just rulers, but sometimes beakers and graduated cylinders will do the same. So in order for us to collect proper measurements, if our beakers or rulers expand, it would be difficult to get a correct measurement. And let's be real, we're human. We make mistakes too. So sometimes it could be just due to operator error. Human error is part of that uncertainty as well. So what are the effects of not knowing our measurements exactly? For some measurement, uncertainty is relatively unimportant. Inexact mass doesn't matter when you're riding a seesaw, okay? It only matters that one person is heavier than the other and that you're able to balance that with force. However, this is kind of a rude one, some measurements are incredibly important. Having something off by a small amount is actually what caused the, and several, not just one, explosions of spacecrafts. So calculating a load accurately on space would be incredibly important, because if you don't, that changes your trajectory, it changes your flight path, it can do all kinds of crazy things. So while some things like a seesaw don't matter how accurate you are, some things truly matter. Engineers will design products to fit certain requirements. If you look here, you can see that there's kind of some plus or minus things happening. Some metal parts may be required to fit together with less than 0.1 millimeter of uncertainty. Engineering tolerances specify the allowable uncertainty. If it were to exceed that uncertainty, the product would not work. So accuracy, it indicates how closely the measurement corresponds to the standard or true value. So accuracy is about finding true value. So a meter stick would be inaccurate if it were accidentally manufactured to be 1.0 yards rather than 1.0 meters. Okay, so this, we're supposed to have a meter, instead we have a yard. No, meters and yards are not the exact same thing. So this would be an inaccurate meter stick. Precision, on the other hand, is an indicator of the exactness of a measuring tool and measurement. So some measuring tools have finer graduations that allow for making more precise measurements. So precision, we see here, this ruler is going to be more precise because it has more graduations on it, so we're able to see close, like a closer view of exactly what we're measuring. With precision as well, typically this is going to show us how consistent you are in measuring. If I were to look at a measurement and give an give 1 meter, and then someone else came up and said 1 meter, that shows that we are all being close to precise. Whether or not that is accurate, we don't know necessarily, because that is more of a device issue. So the precision of a measuring instrument really determines the number of decimal places for a measurement made with it. So of these, which one is going to be more precise? This one, because it has 3 decimal places in it. We're able to go that far definitively in our measurement. So then we can be more precise with our measurement. So looking at this, you can be accurate but not precise. If you have a meter stick with no graduations on it and you're just measuring 1 meter, that is an accurate device. That is very close to true 1 meter. You can be precise but not accurate. If you don't have a tool that is correct for what you're measuring, then you can get the same answer over and over and over again, but your device is going to be the problem. Ideally, we are aiming for both having an accurate measurement, meaning that it's close to true value, and precise. It has a lot of graduations. We're consistently getting close to the same result. And this is what you are going for. Significant figures are digits used to write a measured value. The number of significant figures tells you the level of certainty and uncertainty of any measurement. We use significant figures, and that will tell us actually a lot of information about the measurement tools that we use. For example, here are 2 measured values written in correct scientific notation. So here, this says scientific notation. This one is not written in scientific notation. Never trust the book, kids. So here we see a measurement that's taken at 1.965 meters per second. This measurement will have 4 significant figures. We see 4 numbers here that all correspond to some measurement that was taken. Versus this measurement, we ignore the exponent part of this, and we see 2.4. This one only has 2 non-zero numbers, so this one only has 2 significant figures. Notice that because of this decimal point, we know that this is going to be the more precise measurement. So here are some rules to help you out when you're determining the number of significant digits. Zeros in front of a number are not significant digits. So if we have 5 meters and we were to use dimensional analysis and convert that to kilometers, we would see these zeros in front of the number. They are just placeholders. They are not significant for us. So both numbers have just a single significant digit no matter what you do. Because this is only 5 meters, this is going to be 5 kilometer, or 0.005 kilometers, sorry. Changing unit never changes the number of significant digits. This is why zeros in front actually, or behind technically, are not significant. Because basically that's just telling you it's a conversion, or you could convert it. We only use significant figures when we are talking about measurements. If you are saying I have 6 eggs, the 6 eggs are not significant figures. That's not a measurement. So, additionally, count the number of significant figures in these. Do not include zeros to the left, and do include all other zeros. So for example, I'll do this one, you'll do the next one. We have a 0 in front and a 0. We have 2 zeros in front here, and then a 7, 3, 6. This would be 3 significant figures. Pause and try to do the next one on your own. When you're ready, go ahead and begin, and I will talk you through the number of significant figures you should have had. So this one, we don't have any zeros in front. Okay, that's fine. So then I would count 1, 2. Now while this is a 0, it's not in front. So there are no leading zeros, so I would count it. So this one would be 3, 4, and this one is a little weird, but we'll count it as 5 because we're talking about this specifically. So this one will have 5 significant figures. So when you make a measurement, you may have to estimate a little bit of uncertainty here. So when making a measurement, you may have to estimate to one more subdivision than the smallest marking on the measurement. This estimated digit is still significant. So if we're looking at this bolt right here, or this screw, we see that it's at least 20 centimeters. It's 23, but not quite 24. It might be right in the middle there. So this would be about 23.5 centimeters. 23.5 centimeters. Don't trust the book, kids. And has 3 significant figures. The significant digits include every digit you are sure of and one final one. So when we are measuring, you want to measure everything you are absolutely sure of. We are sure that it goes to 23, but we're going to estimate one more place to that 0.5. So quantifying effects of uncertainty, the result of a calculation can never be more accurate than the individual measurement that went into it. So whenever we are actually doing math, our answer cannot be more certain than the numbers that we put into it. So it says here, a bystander reports that it took about 3 seconds for a car to race down a 100-meter track. We want to know what the speed of the car is. So if speed equals distance over time, our distance is 100 meters. I would put that on top. It took them time, 3 seconds. 100 divided by 3 will give you 33.3 repeating meters per second. But what's wrong with that answer? And what should the correct answer be? Well, if we keep repeating these 3's, this is going to be more certain than any of our other measurements. If we're looking at these 2 numbers here, 3 only has 1 significant digit in it, significant figure. So our answer cannot be more accurate than that. So we would have to then round this to meet that standard. So looking at how many figures would be in 216,500 meters. Well, this way we're not sure if those zeros are going to be significant or not, or if that was rounding or where this happened. So the way that it's written, we're not really sure exactly what these zeros mean. So instead, what we can do in order to show the correct number of significant figures, we can use scientific notation. If one of those zeros is significant, that is where we actually could measure to, we would include that in our scientific notation. So instead of just being the 2.165, we will include that zero. And anything that is written this way counts as a significant figure. You do not count the times 10 to the fifth, that's just placeholder things. But instead, this shows you that I can count all of these as significant figures. So when a number is written in proper scientific notation, every digit that appears will be a significant digit. When you are multiplying sig figs, round the final value to the least number of significant figures. Okay, so if I'm looking at these two, I don't count leading zeros, so this one has 2 significant figures, this one has 3. My answer should only have 2 significant figures then. This also works for division as well. For addition, what you want to do is you want to line up your places, okay? So that way, everything is lined up here, our place values. There is do not add zeros, just line them up like this. And then once you're done, look for the measurement that has the fewest decimal places. So decimal places, this one only has only has 1 decimal place, has 3 significant figures. So your answer will only have 1 decimal place. Now, don't count the significant figures. I said this one has 3, but that's really kind of irrelevant because this could have been 124.9. Potentially, and we would still include this 1 decimal place. Now think about that, because when you're measuring, you round to 1 more decimal place than your device goes. Well, this is just showing how accurate that is. Remember, your answer cannot be more precise than your measurements were. So this is kind of a way to show that this was the least precise of our instruments. So we can only measure that far. Direct and indirect measurement, you can easily count the number of buttons on a coat. That would be a direct measurement. You can count the number of stools in the room. You can count the number of people in a room. But indirect measurements, we can say things like there are 200 billion stars in our Milky Way, but nobody has sat there and counted to 200 billion. So how do we actually know that? So we are going to do this, I think next week. We're going to try to take some indirect measurements and see kind of how that, how we can do that. And then use information that we gather to see exactly how we can estimate a measurement like that. So I'm going to skip through this investigation part. So when following safety procedures, it is important to follow every step in the order that's listed. We've talked about this. This is just safety stuff right here. So I'm going to kind of fly through that since we've already done this, and following instructions and why we do that. So assessment, you are asked to measure a small quantity, less than 5 mils of an unknown liquid. You have 2 graduated cylinders. One is 100 mil and one is 10 mil. Which cylinder should you choose and why? And what possible operator errors could affect the uncertainty of your measurement? Obviously, because this is a small liquid, less than 5 mils, we should use the 10 mil cylinder. We'll have finer graduations and allow for a more precise measurement. An example of a possible example, not reading the measured value at eye level could cause some uncertainty. With water, there is a meniscus in a graduated cylinder, so not measuring at the bottom of the meniscus. There's all kinds of things that could lead to operator error as well. You're planning to knit yourself some mittens. You measured the width of your hand to be 7.3 centimeters. The first one is identify possible causes of uncertainty in your measurement. And what effects might that uncertainty have in your mittens? So the one uncertainty is the width of your hand is not the same everywhere, right? If you look at your palm, there's going to be part of it that's a little bit wider than others. And then what effects you might have mittens that don't fit. So using a caliper, you measure the width of a pencil to be 0.0345 centimeters. Write this value using scientific notation. Remember, this is where you move the decimal point. So I would move it 2 places to put one non-zero number in front. So I moved it twice, so 3.45 times 10 to the negative second, because we moved it to the right. And then how many significant digits are there? If we look here, 1, 2, 3. We're certain of that. That is the end of this presentation. I will be posting more videos about this section later next week. This is the only one you have to do today since I am not there. Thank you and have a good day.